All right, good afternoon, everybody. My name is Freddy Chiu. I'm an AI frameworks engineer at Intel. This is Vasanth Tovinkere. He's an Intel principal engineer, and we're here today to talk about profiling your agentic AI on Windows. So the agenda today is going to be why profiling agentic AI workflows is important. Then we're going to go and profile a simple agentic workflow. And as agentic workflows go, they use a lot of AI tools. So we're going to look at profiling AI tools. We're going to do a demo, and then we're going to wrap it up, summarize, and go Q&A. So why is it important? You know, we're in a very interesting inflection point where some of these very powerful models are running on AI PCs. So form factors like this ones, laptops, there's a lot of power now that you can do, with AI PCs. So the productivity is really going to be measured based on the iterations that you can do with your prompts, because as we all know, getting the right prompts is the key to getting the right outputs. But when you're running these things locally, the key and the function of success is going to be how many iterations of these prompts can you do on the system, and how fast can you do them. And that's why it's important to optimize your workflows. So let me show you here a simple agentic workflow. And what this thing is doing is I asked it to do a 3D model for a wheel. It has specific sizes like 5-inch in diameter, 2 inches wide, and a bore in the middle. And so what this thing is doing is it's running locally on an AI PC. It's powered by OpenVINO and OpenVINO Gen AI and the latest Panther Lake generation. And it's running a Qwen 3.6 model, 35 billion parameters. And as this is reasoning, it's creating a plan for execution. It's creating code. And as part of the tool calling, it's going to use OpenSCAD to render that code into a 3D model that you can then take to a 3D printer. Now, after that, the agent is going to create a stylized version of that image so that you can get a photorealistic version of what it could look like. And finally, once the prompt turn is towards the end, it creates a summary of the conversation so that as you continue to interact with the agent, it will have the ability to remember the conversations. Now, this is a very typical pattern of agents. It reasons about your request, it creates a plan for executing to the request that you asked it to, and then as part of that plan execution, it carries out a set of tasks. And these tasks, increasingly, they are becoming more and more complex and more elaborate. Some of these tasks may call tools as simple as write file. Some others may be as complex as embedded several models that are chained as part of the tool. And so now that we know, what agentic apps do and how to look at their workflows, how do we now start profiling them so that we can actually optimize them? So I'm going to pass it on to my colleague.
Hi, can you guys hear me? So this next section is more about how to get the necessary data for you guys to make the decisions that you have to make. And typically what happens is, for you to understand the software and the system behavior, you need to be able to get the right kind of telemetry from the right places. You cannot optimize what you cannot see. So basically there are two streams of data. You have the platform and infrastructure-based telemetry that is specifically coming from all the various IP blocks on the system, CPU, GPU, NPU, power, networking, Encore, and so on. This kind of data is very structured, and these are system metrics. These counters have been well defined. So the data that you get is structured, and it's low volume generally, and it also has very low overhead. So if you want to get the platform telemetry, it's less than 1% most of the time. And when it goes to the application and middleware, this is a little bit, it varies a bit. It depends on how much of the code is instrumented, whether it's instrumented well or not, or it's just a lot of data that's coming out of it. This data is primarily unstructured. It's higher volume and has higher overhead. Right? So how do you combine the two and try to make sense of it? When you're getting these kinds of data, you need to bridge the physical hardware performance with the software layers that are executing at a higher level. So you have to correlate. The correlation part is the key. And when you look at it, the platform infrastructure is coming from multiple drivers. The drivers are operating in different time domains many times. So what we have in this particular demo is we have something called a unified telemetry that puts them in the same time domain. It's all time correlated. You get the data from the CPU, GPU, NPU, and power. And if you want to get some OS-specific stuff, you can incorporate ETW as well. From the application side, we're going to incorporate the tracing through ITT or Intel tracing, instrumentation and tracing technology. This is an open source project that's been around for a long time. And a lot of the Intel stack has been instrumented with this, right? You know, your OpenVINO stack, 1DNN and other things that are a part of the AI stack have all been instrumented with this. And over time, we're going to be enabling more and more layers. So this is where we're getting some of the software telemetry, in addition to whatever has already been instrumented. And that is the capability that unified telemetry is going to provide. So how is it different from what we have today, right? So unified telemetry is in preview starting this week. But previous to this week, what was different? We would get data from different drivers at different rates in different time domains, and it was the responsibility of a tool chain or a tool to put them in the same time domain. And that was always a complex problem. So if you wanted to do it yourself, problem, right? Because you had to rely on a tool. So it was tightly coupled with a tool. So we are decoupling it, so you get the data from the platform, and it's time correlated. And for the software introspection, you know, there are multiple ways to get the data you want. When an important event happens, you can walk the call stack, figure out who's executing, or you can instrument the relevant portions that are important so that you can correlate the platform telemetry with what's important that's happening in your stack. And that way you can get the right visibility. So in order to do that, you know, this relies on the ITT API, which has a C API, a C++ API, and a Python API, and so on. But that's an open source project which is used in majority of the Intel stack.
So based on the information that we just learned from Vasanth, let's take this into practice. The example that we showed earlier with the 3D printing, agent, if we were to instrument it, let's look at, what we're doing. First thing, we asked it to create, the wheel. So the agent is processing the request and is generating the code. The first tool call is going to be writing the file. So the code that it generated writes it into a file. And then after that, it's calling a stylizer. So after the, code is created, it rendered, it passes it through a stylizer. In this case, it's running an LCM DreamShaper diffuser model. And everything so far, if you notice the lower line that is indicating the power usage, everything is running on the GPU. So we'll talk more about how to fix this, but right now everything is running on the GPU. And so as the stylizer is running, that generation, that orange bar that you see, took a pause, right? Because it's computing the stylizer. And then after that, once it's done, it'll go back and create a response to respond to the chat. And what you're seeing now is that we're about to finish, and this summarization part of the prompt kicks in. So now it switches the model to run a 𝗦𝗽𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀 3.8 billion. And it's also running on the GPU. And so from the user point of view, you enter the chat prompt, and then now you're waiting for the agent to finish before you can start the next prompt. And so now you see that little gap right in the middle, where as I type the next prompt, that's when you process again and then summarize and so on and so forth. So understanding how hardware and software is behaving at a system level is super important, because as we start looking into possible optimizations, let's apply some simple tweaks and see how we can change this. So now, a simple set of optimizations that we can do. The first thing, everything stays the same. We ask for the prompt, the file gets created, and the tool gets called for rendering. Now, for the stylizer, now instead of running that on the GPU, we're delegating that to the NPU. So now you see the spike in power usage at the bottom because the NPU is activated, So that's one benefit. But the other benefit is that the agent, the orange line that you see towards the top, now it continues to generate. Because as soon as it delegated that offload to the NPU, now it's creating the response to get back to the chat. So the next phase is a summarization. As the turn essentially completes, the agent kicks off the summarization of the conversation, and that is done in the background by the NPU. And right at that point, the agent is ready to process the next prompt. And so the end effect is that we can shorten the time from a user experience point of view, and the agent is able to respond quicker. While at the same time, because the NPU is designed for low power and high efficiency processing of AI, while these things are happening in the background, overall you get the same effect, faster turnarounds, and also lower power. So when you're working on a laptop like this translates to higher number of turns that you can do before the battery runs out, and just faster experiences. So, we talked about the tuning that we can do at a system level and how this impact your agentic flows. Now, let's look at the tool calling, because a lot of the tools that agents are starting to use are more and more complex. So, invoking a 8 billion parameter model, diffuser model, and they can get more and more complex. And increasingly, these tools, it really boils down to the end profiling the inferences, because there's going to be a series of pipelines probably in your application, the tools. And so let's look at what we can do for optimizing the tools. And so for that, let's dive deeper into tracing. And Vasanth?
So, we talked about the two different telemetry. So when you're tracing software, I said it's generally unstructured, right? How do you bring some structure to the software traces? Right? If you can bring some structure, you can then run your AI models on it to get the necessary analysis done for you. So in this case, this is how OpenVINO has been structured. So there are different layers of the software. The top level layer is where the phases of OpenVINO execution happens, and they're generally under the OV phases domain name. So when you're doing a query, even in JSON, if you can ask like any of the AI models to say, look at the domain OV phases and then give me a report. And it can give you the breakdown of the top level. And then you can go deeper and deeper with it, right? So the idea is organizing the software traces in some fashion so it becomes friendly for AI and for queries in the future. So if you look at a sample, this is the data from one of the model execution. This is what it'll translate to from a software traces perspective with OpenVINO using the unified telemetry. The top part is the GPU execution, and you're seeing the same kind of behavior where there's an inference. I've taken an inference snapshot, and the bottom portion is an inference on the NPU, right? So you'll see the data is very different. The GPU is less chatty, NPU is a lot more populated because it has different units that are all pipelined together. And so this is the kind of data you're going to get. You're looking at the top level analysis to figure out how efficient your queries were, or how efficient your inferences were, time to first token and then decoding rate and so on, easily can be computed from the top level query. But if you want to get to the operator level specifics or the layer level specifics, you'll have to go into the next level of detail. And how does it tie with the platform telemetry, right? So this is the kind of platform telemetry you're going to get. This is basically displaying about 1/10 of what you get. You get a lot of platform telemetry. You get the memory reads, memory writes to DRAM, IP block to IP block, bandwidth. You'll get power, you will get the utilization and so on. So you can correlate your AI model execution with any of these metrics to figure out how you would want to optimize it. So from that perspective, unified telemetry gives you a mechanism to get data from both. Of course, when I say data from the software side, it's still based on the ITT tracing information and the telemetry from the drivers. It combines both of them into a single time domain, time synchronized output. Currently in JSON, this is the first preview of it, starting this week, and over time it'll probably have a database around it as well, a vector, a column database, so that queries can be more efficient. And right now, the OpenVINO runtime is fully instrumented, and we are trying to add additional layers on top. And so the next section is going to look at what would happen if you, instrumented the Windows ML layers and so on, and then how do you combine the data together. So that's what the next section is going to look at. To instrument your own software with the ITT API, the open source project builds a static library that you can link in with your application and causes no overhead until you attach a tool like Unified Telemetry to collect the data. So it's basically putting certain markers in place that are there when a tool attaches for you to get the data. And in this case, we are, creating a domain called WinML samples, and then creating a task underneath that called session creation, which is what will show up in your data. So there are two different tasks that are shown here, session creation and inference. So this is how most of the Intel software stack has been instrumented, and if you want to extend it beyond the layers that are currently visible, you're welcome to extend it to the layers that are of interest to you. So that brings us to the demo, and Freddy will take over.
All right. So what we are going to do is I have an agent running. It's a 3.6 billion parameter model. It's a Qwen 3.6. It is running on a Core Ultra Series 3, all locally at the time. And let's say that you had a tool that was built with Windows ML. And I am going to ask it to essentially profile Windows ML tool running conf next v2 on GPU FE16 for 50 iterations. So what this will do is we have equipped the agent to use tools to basically enable the tracing session that Vasanth talked to you about. And it's going to profile the tool that you developed that is instrumented now also with those markers at the application level. And it's going to correlate all the hardware events, all the underlying frameworks, right? The OpenVINO events, all that stuff is going to be created. And then data is going to start surfacing. The agent is going to process the data that comes out of it. And it's going to give you a summary, right? Now, the data generator is going to be super helpful to start dissecting whether this model is efficient, whether this model consumes a lot of power, will it be good for your usage? And depending on what you're trying to accomplish with your application, there's different ways to tackle it, right? And different ways to optimize. So in this case, what it did is it created a summary, and it's tallying the performance, the latency. It is also giving you some level of variance, so the maximum, and it's giving you the average inference. So running this model itself and this tool took about 9 milliwatts. And for more details, right, it also provides links so that you can see a more detailed report of the execution of the model itself. But it also interpreted this data and provided you some summary, like latency, if you care about it, right, you may have some considerations to make. So let's look at the trace file. Now, this is the tool and application that we have already instrumented. And so if you zoom in, you can now see some of the Windows ML application events that we traced and we added to the application. So you can clearly see now there's a correlation between what the app is doing and then the underlying hardware execution. And you'll notice that there's a bit of time that is spent on model compilation, and then there's all these little events over here that if we zoom in, we can actually determine and see what is happening. And from a software stack point of view, this is what OpenVINO is doing, is handling your inference. If we zoom out, you can now correlate the hardware activity. So let's collapse the host trace, and if we look at the GPU, we see that these are the corresponding hardware events. And these are all the different kernels that are getting executed. Now, why is this useful for a developer? Having seen this, knowing that there's a capable GPU sitting on, on your device, one of the things that you can do to optimize this is you want to get to the inference part as soon as you can. And so one way to, for instance, to get rid of the compilation time or reduce it is to pre-compile your model. So if you pre-compile it, you can reduce significantly this model compilation time that you see here. And so your tool will execute faster, right? So this is now very powerful. And the next question might be, OK, so you optimize the compilation part, but is this model the right model? And if you are dealing with model optimization, you know that you have a lot of choices. There's different data types, like FP16, Int8. Now we have NPUs. And so is picking the NPU the right device? Is GPU the right device? So now we can ask the agent to also do this profiling across multiple workloads. So let's ask it to do a comparison. Let's do a tiny YOLO. Oh. 11. So I'm going to ask it to profile YOLO v11. I have an FP16 version and an Int8 version. I have an NPU and a GPU. And so there's 4 combinations, right? So the agent is reasoning in this case and conducting a plan. It'll ultimately execute 4. And I'll bring up the task manager so that you can correlate what the agent is doing at the time. OK, so what you will see is that as the agent creates a plan and starts the collector session and the workload session to start tracing, it'll do that one at a time, because every time it collects traces, there's a lot of data points that gets generated. So it has to process some of the binary files, the log files that get created. It creates a summary, and then it'll aggregate the combination of all those results, right, and give you a summary of all the workloads that we just run. So you'll notice that the GPU ran for a long time. It was processing and doing the planning. Then you see a short spike after that. That's essentially the agent profiling the GPU scenarios for these workloads. You'll see a couple of tiny spikes on the NPU, and each one of those instances is essentially the agent running that FP16 model on NPU, and then again running it on the NPU, but with Int8. And for each of these sessions, you have to start and stop the session because the amount of data generated is just incredibly high. So once that is available, there's all this operator information that gets extracted, and now we can start looking at their profile. So let's see what the agent generated. So it's compiling a table of the inference latency for each of these devices, and also the power used for each of these devices, the energy, and then the peak wattage, right, during those periods of time. And based on the results, it's also giving you real time, right, the recommendation, like some things to consider. If you are looking at speed, that is more important for your application, then consider the GPU. If you want more energy efficiency, and maybe it's a task or a tool that you can do in the background, then the NPU is better. And so with all this information now, you can do a lot of trade-offs and optimization points for your tools. OK, I'm going to switch back to my slides. OK, so the summary is, for agentic workloads, we need to profile them. We need to understand what they're doing and what the system is doing as a result of your agent. Then you can start analyzing, right, where the time is spent. And finally, you can start tuning and optimizing their workflows. Where can you parallelize some of these? Where can you offload? Where does it make sense? And then you can optimize their tools, which is where a lot of the time is going to be spent also. So the call to action is start adding traces to your agentic flows, and using the unified telemetry you can now take this data and put it into action. There's more information here about the Intel Unified Telemetry Framework, the ITT API for instrumenting your apps, OpenVINO and OpenVINO GenAI, and then Windows ML, which underneath uses OpenVINO for powerful inferences. And last but not least, Windows ML CLI, which gives you the capability to do operator profiling, Onyx operator compatibility. And we'll be on later on tonight hosting a party, so please join us. It's going to be at the SF Brewery at 7 o'clock. So looking forward to see you all. Thank you.
If you guys have more questions, we are at the demo booth, and we probably have the same demos. We have access to unified telemetry, so if you want more about it, you can come and check it out.